Hey everyone, quick video coming at you here. Um, I have all the different types of solution problems and topics that we've been discussing, and I have them broken down by heading. I'm not going to do every single one of these. I'm just going to do maybe one from each section to try to get you some strategies on how to solve these if you ever see them again, and you will. First thing we ever did was something called dissolution or dissociation. Let's pretend that you have compounds that dissolve in water. What do they make when they're in water? Okay, so the first one is something called barium hydroxide. Guys, you should know how to generate a chemical equation based on the name or formula. Um, so I'm going to skip that. I just know that barium hydroxide has this formula. Now, solubility rules can be used here, but I say that it dissolves in water, but here's how you would know that it does. And I'm going to bring up this table just for uh, introduction because we will use it later. Most hydroxides don't dissolve in water unless they are paired with ammonium, any element in group 1, barium, or strontium. And so this is a soluble exception to hydroxide insolubility. At any rate, when it's added to water, water will break apart the ionic compound. And so I'm going to show it like this. I'm going to produce a barium 2 plus ion. And I would know that because barium is in column 2, right there. So it's going to be a 2 plus. It's also going to produce 2 hydroxide ions with a negative charge. And these are both going to be AQ, indicating that we know they're within the aqueous or dissolved phase. So those are pretty simple. This can tell us that for every 1 mole of barium hydroxide added to water, 2 moles of hydroxide ions are produced. And in a later section, we learned that the definition, or one definition of a base, is the ability to produce the OH ion in solution. So that's dissociation. On to the next one. How to make a solution from a concentrated stock. I do this all the time. We've done it before. Basically, you're going to use the M1V1 equals M2V2. When you set this up, every time that we're making a dilute solution from a known concentration, we're always looking for V1 because my initial molarity is a known molarity here, and it just happens to be 18 molar. Pretty strong. Stronger than you would need for most applications. However, it's very favorable because it cuts down on shipping costs. They send a very concentrated bottle, and then you can just make a bunch of dilutions later depending on what your needs are. I don't know how many milliliters or liters of that concentrated solution I need to add to get a molarity of 2.75 molar with 850 total milliliters of volume yet. So that's going to be my question mark. But I do know what my target molarity is, or what I really want, which is 2.75. And I know that I want the final volume of that total solution to be 850 mils. In a question like this, you really have to find two things: how much concentrated acid or base or whatever you're going to need to add, and how much distilled water to get to this volume. So this is my equation. I'm looking for V1. Let's divide both sides by M1 and get there in one step. Makes it a lot easier. So this is only going to tell me letter A. You don't need to change into liters because I'll show you why in a second. So I have my initial molarity, or sorry, my final molarity of 2.75 molar. That's moles per liter, times my volume 2, which is 850, divided by my known or concentrated stock molarity, which is 18 molar. This would be better left in milliliters because it's a more comfortable unit of measure for dispensing solutions. Liters you could do, but just go ahead and leave it, and then you can change it later if you really want to. 2.75 times 850 divided by 18. Okay, I need about, let's go with the number 130 to keep sig figs correct because this one has 2. I need 130 milliliters of concentrated acid. Now I want my total volume to be 850. So to figure out part B, I'm going to do this. Just do this down here. It's simply 850, which is the total volume, minus the 130, because that's the acid that I had to add already. So 850, 30, I need 720 mils of distilled water. Okay, another type we did, let's say we didn't have a concentrate. Maybe we had a solid solution. In the case of a solid, you're going to use a volumetric flask as well. We talked about the best strategy to do that. You add about a third of water, add your solid, swirl it around, then fill to that line. Most volumetric flasks have a line about a third of the way up the neck. So here, I want to figure out how I would make a solution with this molarity at this volume. You're going to need a formula here because we need grams to add. So I need to find grams. So oxalic acid's formula is shown here, C2, H2C2O4. Now, you guys should know how to take a molar mass, so I'm not going to show you how to do that. The molar mass of oxalic acid is about 90.3 grams per mole. All right, so let's start with the molarity here. I want this target molarity to be 202.5 moles per liter. Remember, the capital M just simply means moles over liter, 2.50 moles of oxalic acid for every 1 liter. I want to figure out how many grams I need, because this volumetric flask is calibrated to give me 500 milliliters. Now, this would be helpful if I could envision this as a liter volume to get a cancellation here. So I could have 0.0 liters to cancel. Simply just change that to liters by dividing by 1,000, move the decimal place 3 places to the left. Not hard. And I know that the molarity of oxalic acid is, the molar mass is this many grams for every 1 mole. So that's going to go away. And now I think I should have the amount that I need, which is the gram value I need to add to this flask filled to the line to get that molarity. 2.5 molar. 0. I need about 113 grams. I'm going to show 3 sig figs here because this number has 3 sig figs, and here's the calculator output. So I need 113 grams of oxalic acid. All right, flip it over. Let's try to get the other ones done as quickly as possible. These were stoichiometry type problems. This should say stoichiometry. You need a chemical reaction and chemical equation to even begin this. So let's do that first. Iron metal is going to react with hydrochloric acid to make iron 2 chloride, ferrous chloride, hydrogen gas. So there we go. Let's put a 2 right here to balance this out. I think we're done. Okay, let's start with the 3.25 grams of iron. Let's convert to moles. There's iron right there at 55.85. Here. If we can convert to moles, then we can use the mole ratio, and then we can use the molarity to get where we're going. There's 5 grams of iron, 1 mole of iron. There goes grams. For every 1 mole of iron, I need to use 2 moles of hydrochloric acid. Now, this means moles per liter. So the orientation of this is going to be important. I'm going to flip this because I want moles to cancel. So I'm using a solution that contains 3.25 moles of HCl for every 1 liter of solution used. And now that I have liters, I can figure out how to get to milliliters easily by just multiplying by 1,000. There are 1,000 mils in 1 liter. I'm not going to count that as sig figs. Same with the mole ratio. Those are simply relational values, not measured ones. Here we go. I need 35.8 milliliters of this concentrated acid to completely react with that many grams of iron. That's a really helpful thing to know how to do if you're trying to predict what you'll need for any given process. Let's show 3 sig figs here. So 35.8 would be just fine with me. Milliliters HCl. Lastly, I know this video is running into 10 minutes, but this will help us with titrations, specifically where we have a neutralization reaction. In a neutralization reaction between an acid and a base, the key event here is the formation of water. So I know that sodium hydroxide is going to be my titrant that we use frequently. You can use an acid as a titrant. We haven't done that yet. Sodium hydroxide can be added to sulfuric acid. This is going to look very similar to a double replacement reaction, where hydrogen and the metal are going to switch places. This will form water, which again is the key distinguishing characteristic of a neutralization. So the formation of water here is going to occur. I'm also going to form something called sodium sulfate. Let's balance that out. There we go. All right, in a titration reaction, we're going to use the M1V1 equals M2V2. Why? Because I know that the titrant has a known concentration of 0.100 molar. And when I have the burette filled to the 0 mark, I have a full burette. And if it goes here, it means I dispensed exactly 23.3 milliliters of titrant into my flask. So that's going to give me my initial volume. Recall that M1V1 is our titrant, and this is going to refer to our analyte. It's helpful to visualize what that's showing you as a point of reference, because in a titration, the titrant is in the burette, and the analyte is in the conical or aluminum flask. There we go. So I know that my volume 1 of acid or titrant used is going to be 23.30 mils. I have an idea on what my volume 2 is going to be because typically that's measured with a volumetric pipette. It's going to be that many mils. What we don't know is my concentration of acid. So we need to find M2. Don't really need to convert to liters here because milliliters will cancel units. 0.1 times 23 divided by 25. Here's my molarity, 0.092 molar. And that's how a titration works. So guys, hopefully that's helpful with reviewing all the content we've discussed. We'll pick this up tomorrow.